Hey team! So I know last week's discussion post was a bit confusing. I know we're still getting used to thinking about phylogenies and thinking about all of these different evolutionary concepts. So I kind of wanted to give a little bit of overview of how I would have addressed some of these questions in the discussion post. So again, let's talk about kind of what we're looking at. So we are talking about these many different species of rove beetles that, through the process of natural selection, have basically, natural selection has tinkered with their body plan so that way they look like ants, they even smell like ants. And so that allows them to live within these ant colonies, basically undetected. They're kind of like parasites in a sense, or like a wolf in sheep's clothing, right? So typically, these rove beetles, some of them would go into ant colonies, eat a few ants or a few larvae, and leave. Now, these ones that natural selection has tinkered with their body plans, and these mutations have arisen that let them look like ants, right? This ant mimicry, Myrmecoidy. Now, they have basically an endless food source. They can exist within these ant colonies, eating all of their different larvae, basically just hanging out there undetected, right? So that is a huge advantage, right? You basically get a free food source. You just gotta hang out and look like an ant and smell like an ant, okay? So that is rove beetles that are able to mimic ants probably have a higher fitness because they're gonna have more food available, which means that they're gonna have greater likelihood of having energy available to reproduce, right? And so kind of diving in and digesting this phylogeny is challenging. One, because it's so small and there's so many different lineages. We're not used to looking at such huge phylogenies like this. And two, partly because a lot of this is hypothesis. And we're missing a bit of information from the background from the paper. So if we're looking at this right here, in the orange, these are the ant mimicking lineages, right? So it looks like to me that the very first lineage that arose would be this one right here. Okay, so let me zoom in on that. So if we have our time, these are millions of years ago, so 25 million years ago, 50 million years ago. It's usually MYA is what that's abbreviated as. So to me, when I'm looking at this lineage that emerged right here, looks like it was the earliest one to emerge. And if we were to take a ruler, or what I did is I took a piece of paper, kind of held it up and said, okay, where does that line up? So it looks like, when does this divergence happen? So to me, with my piece of paper, it looks like it's about 70, I don't know if I'm holding it level, probably close to around like 70 million years ago, roughly. Definitely before the Cenozoic era. Okay, so we can use this time scale on the side to estimate when these different branchings happened. Okay, so I would say around 70 million years ago, roughly. The other part of that question is, how many different ant mimicking lineages are there? Okay, so if we look at a lineage being all these orange pieces, we're not counting species here. If we were to count the tips of each of these branches, we would be counting species. The reason why we're going to count, for example, this clade right here, this group right here, we're going to count this as one lineage because they inherited, because they're all connected together, they all share a common ancestor right here. They inherited that ant mimicry from their common ancestor. So this is one lineage, one grouping of ant mimicry. Okay. If we do that, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. And I know that the video said that there were 12. Okay, so if we're counting this way, we get 15. I'm guessing, see how close, how many in this one clade right here? If we start right here, we talk about just this clade. This group has ant mimicry, this group has ant mimicry, and this group has ant mimicry. So in this clade, there are more species that have ant mimicry than those that don't. So it's probably more likely that this common ancestor was an ant mimic, had that trait, passed it on to their ancestors, and that these species in this group that are not ant mimics have secondarily lost that. They reverted back to the original state of not being an ant mimic. So we could probably call all of these, this clade right here, as one lineage. And I bet you that's how they got to 12. Okay. Or it may have been, yeah, it's probably that lineage. Or could be this one as well, but that wouldn't get us to 12. Okay, so it's probably that this grouping right here, accounting as one lineage. But it's a hypothesis. It's just our best guess. We would probably get more information if we were to dive into the actual primary literature paper, but I didn't want to overwhelm you with that. Okay, so now let's think about the other part of that question of, is this convergent or divergent evolution? Meaning, did the common ancestor of these ant species, was it an ant mimic, and therefore all the lineages inherited that trait, and some may have lost it, which would be an example of divergent evolution? Or did these different lineages that are highlighted in orange come upon this ability to mimic ants, this mutation? Did they come upon it independently? Meaning they didn't inherit from their common ancestor this ability to mimic ants. Unique mutations arose in each individual lineage that led to them being able to pretend like they're ants. Okay, so if this common ancestor right here had been an ant mimic, we would probably see a greater number of ant mimicry clustered together and probably fewer individuals that had lost that ant mimicry trait. So if they had inherited this from their common ancestor, if this was an example of divergent evolution, we would probably see the ant mimicry clustered together into clades more than we do, and we would probably see more ants, or excuse me, more beetles that are ant mimics, a higher rate of ant mimicry. This is an example of convergent evolution, meaning they're converging, they're coming together and settling on a similar solution to deal with a problem, or the forces in the environment have selected for, are similar, and therefore select for similar solutions. Okay, so convergent evolution is kind of like evolution repeating itself in a way. You give it the same parameters and you get a very similar solution out, right? So one of the like super classic examples of convergent evolution is the idea of wings and flight, right? So wings evolved once in mammals, once in birds, and once in insects. The ancestor of these species didn't have a wing, it didn't have the ability to fly. These different lineages came upon this ability to fly, this mutation arose independently in each of these groups. Okay, so because of similarities in their environment, similar selective pressures, they evolved a similar solution. Okay, and the reason why we know that this is an example of convergent evolution is because look at how the wings are constructed. The bones that construct the bat wing are very different and very differently arranged than the bones that construct the bird wing. And the insect has no bones at all, right? So they're completely different evolutionary origins, but they have the same shape and the same function, the same basic adaptation, okay? So with these, it's going to be an example of convergent evolution, meaning that this ant mimicry arose independently in this group. It arose once. There was another evolutionary event there where this ant mimicry arose in each of these different lineages. Okay, that doesn't seem very likely, but they were faced with very similar environmental pressures, very similar selective forces, and they settled on a similar solution. Okay, so this would be an example of convergent evolution with ant mimicry. So some other examples of convergent evolution, there's tons of different examples. If we think about the mammalian eye or the vertebrate eye and how the lids evolved, that also evolved independently in some cephalopods. They have an eye that's very similarly structured to ours. Us and koalas have fingerprints. Apes and koalas have fingerprints. We think that has something to do with grabbing leaves or something like that, right? The shape of animals that live in the ocean. Think about the fusiform shape of dolphins and whales and sharks and fish. That is all a result of convergent evolution. Those same forces shaping life in the water resulted in that's the best body plan for these organisms to have to survive, right? So it's lots of different examples of convergent evolution, but the key is that they're different evolutionary origins, but they're coming to the same solution, the same adaptation. Okay. All right, I hope that was helpful. I know that this was a lot and you may have felt that you got thrown off the deep end. I totally get that. Working through it and making mistakes and maybe not totally being sure, that is part of the process of learning, okay? And that feeling of being uncomfortable, that's okay, that's good. We only grow and learn when we get out of our comfort zone, when we push ourselves a little bit, right? That's how you get better. So good job. I hope this helped.